Welcome back to this NPTEL online certification course of molecular rearrangement and reactive intermediates. In the last 3 classes, I start talking about organoboron chemistry. I talk about the synthesis of different type of organoboron compound. I talk about in the last class about the hydroboration in depth. I talk about the stereoselective hydroboration, the enantioselective hydroboration. And in the today's class, my plan to talk about another important aspect of the organoboron chemistry is the as a reducing agent. There are several different organoboron compounds which can be used as a reducing agent of carbonyl, acid chloride, esters, acid, and many other functional groups. So let's talk about and let's learn this, because this will be an important topic in any competitive exam. So in this class, my plan is to talk about the different type of borohydride. I think you must have heard about this, and then there are reduction using borohydrides. We are going to learn about the difference of different type of borohydrides, then the stereoselective reduction using borohydride, and then we are going to talk about the enantioselective reduction at the end. Okay. So first thing, if you try to learn about the boron and hydrogen, I think one thing you should try to understand once you have this boron and hydrogen, and if you try to compare the electronegativity. So this is 2.04 electronegativity, this is 2.20. That means you can see that if you think about the boron and hydrogen bond, the electron density is always towards the hydrogen. Okay. So that is why you can see the electrons in the boron hydrogen bond are polarized toward hydrogen, correct? So that is that's why if you think about the sodium borohydride, if you think about that B minus, you can think about despite the formal charge is -1 on the boron, it is actually the hydrogen which actually carry the partial charges there. Because what is happening, if you see in a bond, the electron density is lying towards hydrogen. That means the electron density is actually in the hydrogen. That's why you can think about the negative charge is actually lying on the hydrogen, not in the boron, correct? So now if you think about, these are the reagent where you can see that now they can transfer the H minus to different substrates to form the corresponding product. Okay. Now if you think about this, the BH4 minus, there is another important thing which is say Na plus in the sodium borohydride, correct? So that is in the sodium borohydride, but we will be going to learn about. So you can say this is a M and this is a BH4 minus, correct? M plus, I think that is, but M plus BH4 minus. So now depending on the size of M, depending on the metallic character of M, the reactivity of this different borohydride will vary. Okay, depending on the radius and all different things, the metallic character, everything going to play an important role here. So first things is that try to learn about what are the different type of this type of reducing agents are present from the boron. So one of the things is I think I mentioned is the sodium borohydride. You can see sodium with the BH4 minus. It could be lithium, then it will be lithium borohydride, sodium triacetoxyborohydride, sodium cyanoborohydride, then the lithium the BHR3 or the L selectride, where the boron with 3 alkyl group here. Instead of the 3 hydrogen, you see 3 alkyl group here with 1 hydrogen. And then I'm going to talk about the another, I think reducing agent is the boron. I think you have seen there the first reduction already you have seen in the previous class, correct? When you talk about the hydroboration, you see the olefin reduction happen. But then we're going to learn that the boron can not only do the olefin reduction, it can also use for the reduction of the carbon group as well. And mostly you can see the reaction what is happening here. You have this some sort of a sodium or the metal plus which actually activate this the carbonyl group here, which allow now this H minus to transfer here to the carbonyl group. Okay. After that once you quench with the water, you will end up getting to the corresponding product. And the other important thing is in this type of reaction, I think I am going to explain it, the solvent play a very important role here. Okay, so not only the solubility is the part, but also you can, as you understand, these are a charged species, so the solubility is one of the important thing. The solvent also control the reactivity as well. So first I am going to start with the boron, because as you see I have already talked about the hydroboration in the last class. So let's start with the boron. So we have learned that the boron can able to reduce the olefin, correct, to form this type of trialkyl boron, correct. So you have seen that in the previous classes. Now if you see that if you can treat the boron, the important aspect is it can do a reduction of carboxylic acid in presence of the ester. So this is a very important things about the boron. It is not only can be able to, it can It can also in presence of lactones or amides or halides. So in presence of that also it can able to selectively reduce the carboxylic acid. It can also able to reduce the aldehyde, ketones and alkenes, which I have I think I already mentioned that it can able to reduce alkene, but it can also reduce aldehyde and ketone. But the important aspect is the one which if you try to remember boron, then you should remember boron for another purpose of this chemoselective reduction of acid in presence of lactones or in presence of ester. Okay. So let's try to understand. I think we already know that the boron not only comes like BH3, there will be always some Lewis base, like there will be solvent where the oxygen can give the lone pair, or there will be dimethyl sulfide, okay, where the sulfur can give the lone pair. So this can be purchased in the solution of this. Okay, now once you treat with this, if you have this substrate where you have this carboxylic acid and a lactone, and you have this carbon halide bond also, carbon bromine bond, using boron you can selectively reduce the carboxylic acid, and then you can able to make a tetrahydropyran protection. So it will be THP here, sorry for that typo, it will be tetrahydropyran protection going to done of this corresponding alcohol. There is another example here. You can see there is a ester here and there is a acid here. In this vinyl carbon there is a ester and then there is a CH2COOH. Using boron you can selectively reduce that to corresponding alcohol. So now the question arises, why the boron is so selective to the carboxylic acid? One of the things is, once you can think about, once you have this boron which actually immediately can come to the oxygen because boron is electron deficient, oxygen can give the lone pair to form this species B minus. Now this H minus and this H plus from this acid can form H2. That will end up making this RCOBH2, OBH2. And if it is keep on adding to another 2 equivalent of carboxylic acid, it will end up forming this, so there will be oxygen here. Okay, so it will end up forming this RCOOB, whole 3. When what is going to happen at the end, finally the boron will be able to reduce this down to the corresponding alcohol. Because so the chelation of this boron with the carboxylic acid, so that is the important aspect why this boron can be used for the selective reduction of the corresponding carboxylic acid to the corresponding alcohol, which is not happening if you have ester. So this is a list. I think you can try to remember some of this. I think of course we know that if you have I think you guys are already familiar with the sodium borohydride, which is going to give reduce the ketones and aldehyde and acid chloride, correct? But a lot of times I think some student ask me question, or sometime I have sometime I have seen in the PhD students are asking me question that, sir, sometime we have seen the sodium borohydride also can reduce the other functional group. And what happening when you are looking into those reactions, what students are not following, that there are some other things also added. Suppose if you think there is a magnesium chloride and sodium, so if you see a reaction is given like that, where there is a sodium borohydride is written here, and here you have written MgCl2. Now you see something happening in the product which is a little bit unusual, because you always think the sodium borohydride means it will be a ketone, aldehyde and acid chloride. But now as soon as you mix with magnesium, what is going to happen? Now it can reduce the ester, which was not possible using sodium borohydride. And now if you use a AlCl3, you make aluminum borohydride, which can even reduce corresponding acid. So this is a very strong, you can see it can reduce everything in the table. And then if you add a calcium, again you can see it will be very similar to the magnesium, calcium borohydride. And then I am going to talk about the zinc borohydride. Again the zinc borohydride will be much more little bit selective, it will be very similar to the normal sodium borohydride, but there are some other things I am going to also bring them again. Also I am going to talk about this one, the selenium, using selenium chloride for a Luce reduction. I am going to talk about that. I am also going to talk about the sodium cyanoborohydride. Not only they are useful for the reducing of the aldehyde and ketone, but they can also reduce the corresponding imine to form. So for this there is a reaction called the reactive amination. Okay, we are going to talk about that. Okay. And then of course I am going to talk about sodium triacidoxyborohydride. So that another important thing, it can only reduce the aldehyde, but it can also have some other selectivity if you want to control the CO selectivity. And then of course I am going to talk about the lithium borohydride, the another one in this table which is coming before sodium, and the lithium borohydride can itself able to reduce ester. So that means if you have a acid and a ester here, it can selectively take the ester in place of the acid. And then I think the other one, I think of course I think you guys are already familiar with the lithium aluminum hydride, which can reduce every single the functional group here, which I have given here. Even more, I think I have not given you the epoxide and some other functional group. Of course, those can be also reduced. Then the other one is the called a superhydride, is the lithium triethyl boron. Okay, it is very powerful one, very strong. It can even reduce the carbon bromine bonds. Okay. So first thing I am going to talk about the lithium borohydride because of this important chemoselectivity, which I mentioned just in a minute, that if you have a substrate have a ester and a acid, previously I talked about a reduction where it is selective for the corresponding acid. If you remember, I talked about if you take a boron, that is taking to the corresponding carboxylic acid. But if you take a lithium borohydride, it will going to take esters, leaving the acid. Again, what is happening? Why lithium borohydride is selective to the ester in place of carboxylic acid, tertiary amide and nitrile? Because once you have a lithium borohydride going to you are using, it is in case of acid, what is happen? It is going to form a hydrogen by abstracting this proton from here. Instead of going for a reduction, it is going to just go for a proton abstraction. The other thing is, if you have a lactone and if you have a lactone here and you want to go for a reduction, then the sodium borohydride will not go for a reduction here because it's a weaker one. But once you have a lithium borohydride, it is going to go for the reduction of the lactone to form this diol. So what is happening? The lithium borohydride is much more reactive compared to sodium borohydride. So if you try to think about, then you have to understand the Lewis acid strength depending on the hardness of this metal. Okay. So you have to understand the percentage of the hardness of between the sodium and the lithium. So you see the lithium will be stronger compared to the sodium. That's why you can see the lithium borohydride will be stronger reducing agent compared to sodium borohydride. Okay. Then I am going to talk about the zinc borohydride here. So zinc borohydride can also reduce the carboxylic acid to the primary alcohol, but sodium borohydride cannot. In presence of a zinc borohydride, the carboxylic acid can be reduced to the corresponding alcohol, but of course sodium borohydride cannot able to do it. Again, you can think about the Lewis acid character of a zinc versus a sodium. That is also another important factor here. And zinc borohydride can be also used for the reductive amination, which I am going to explain in a minute. Okay, if you have a reductive amination reaction, you can also use zinc borohydride, which can able to reduce the corresponding imine which is going to form here. So it's going to form an imine first, which will be reduced by zinc borohydride to form the corresponding amine. The other important factor is using sodium borohydride, you must have seen that if you are trying to do a reduction of a enone, then using sodium borohydride you will end up getting a mixture. Although this will be a major, means you sometimes depending on the substrate you might get 60-40, or of course, so by changing substrate sometimes you will see a various selectivity you will get. Okay, but the problem is once you get these two, it will be very difficult for you to isolate. So that's why you have to find a condition which will give selectively one product. That's introduced to the Luce reagent or Luce reduction. So here you use a cerium chloride in place of methanol. So solvent is also very important here, because once you use cerium chloride with a methanol, then only you see the selectivity, that it is selectively going to take you to the corresponding allylic alcohol. But again, if you take a THF here instead of the methanol, you will not see the selectivity. You will still see a very much mixture. Of course, little more selectivity compared to sodium borohydride, but not the exclusive selectivity that comes from adding methanol here. Because what happened, first the selenium actually interact with the methanol oxygen. Okay, so it is going to first there is a coordination going to happen with the oxygen and the selenium that makes this hydrogen acidic, because once you have a plus character on the oxygen, you see this here. So that can coordinate with the carbonyl oxygen here. Once you see this H plus is coordinating with the oxygen, now this center, this carbon is getting very much electrophilic. Okay. That's why you can see here it can be also happen that if because of this protonation happening, if you have a aldehyde and you have this aldehyde and you have this ketone. In this particular cases, it is end of giving the reduction of the if you see at the end, you found that your the ketone got reduced, but your aldehyde not. You might be thinking, sir, we not understand that because sodium borohydride can reduce the aldehyde, but that is not the factor here. There is couple of things, couple of important thing happening here. One of the important thing is that once this is, so this H plus is binding with the oxygen, so this can now form say acetal. So the acetal formation will be faster here. So once this is forming acetal, now the H minus cannot able to attack here. So you can see that here it is going to attack to the carbonyl group, and at the end this can get quenched to come back to corresponding aldehyde. Now the other important reason I talk about the sodium cyanoborohydride. So if you see, by introducing a cyanide, you pull some electron density from the boron. So if you pull electron density, then you make the reagent more selective. So that's why cyanoborohydride, you can see it is very selective reducing a reagent. You can see it can able to reduce the corresponding iminium to the corresponding, you can see it can carbon amine nitrogen double bond can be reduced to form this corresponding amine here. Also you can, if you have if you don't have a iminium, if you have a amine, if you have imine only, then in that cases if you have only imine, sometimes you can use a Lewis acid. Okay, so now that can activate, the imine. So now the sodium cyanoborohydride can transfer the H minus for this reduction. Okay. Also this can be done in a if you try to make a imine in the same pot where you can use a cyanoborohydride. So cyanoborohydride is very much stable on this pH. So now if you take cyanoborohydride and you take a amine and you take a aldehyde, this is called a reductive amination. You start from the aldehyde and you end up making a amine here. Every cases you can see starting from the aldehyde you are making a amine. So this reaction called a reductive amination, and this reaction done in the pH 4 to 5 using cyanoborohydride in presence of aldehyde and the amine. So in presence of this pH, what is going to happen? This amine and the aldehyde can form a corresponding imine. Imine will get activated in presence of the acid, that can allow the cyanoborohydride to transfer the H minus to form the corresponding amine. This can not only the intermolecular, that can be intramolecular also. If you have a carbonyl group here, you have a NH2 on the same molecule, you take the exactly similar condition which you end up making to the corresponding pyrrolidine. Okay, you can make able to corresponding 6-member nitrogen compounds. Okay, there is another important reaction here, the sodium triacidoxyborohydride. Again, if you see, we have mentioned that the sodium trioxyborohydride can also do a reductive amination here. You can first form a imine using that, and then if you use a triacidoxyborohydride, that can also able to make amine. Okay, so now I am going to talk about the other reagent called, if you have a bulkier group here, like this bulkier trialkyl group attached with the boron with this hydrogen, with the BH, correct. So these are actually, these are called L-selectrite or K-selectrite, based on the potassium versus the lithium, correct. So these are a very bulky hydroboron. So you can see they are bulky H minus transfer agent, and these are used if you want to do some sort of a stereoselective reduction of a carbonyl group. I am going to show one example here. So if you have this cyclohexanone, you have this this position, in the 4 position you have this corresponding R group. Now there is a, if you try to draw in the chair conformation, now there is a approach can be happen from this side versus the other side. Now if you use a smaller the H minus transfer agent or the corresponding borohydride agent, then you cannot get a good selectivity. It can approach from the either side. But once you use a bulky one, now the steric between this group, if you try to approach from this side, then there will be the steric interaction between this group, the H and the R group with the incoming the hydride source, the corresponding borohydride will be higher compared to if it is going for the bottom phase. Okay, that will end up the selectivity in the product. That means now what is going to happen, if the H minus is coming from this phase, you will end up getting to this product as a major product here using this type of hinder the borohydrides. Again, if you see in these cases what we are seeing here, now this is a, depending on the structure, if you see here you can get two different scenario here. you can get a 86% major product and 14% minor product here. Once you bring some substitute, if you bring this dimethyl group here, now you are kind of blocking this the upper phase more. In that case, you can see your major so what is happening here, let's try to understand in these cases. Now if you think about it, can the H minus can be approached from this phase or the top phase, correct? So what is happening here, once you increase the steric here, the bottom phase approach will be favorable. Once the bottom phase approach will be favorable, you end up giving to this product as a major product. So what is happening here, once you don't have this steric bulk, now if you think about, still if you try to compare from approaching from this phase versus this phase, I think previously I talked about this already, that here you have a 1 CH2 group to sterically interact, here you have a 2 CH2 group. So that's why you see that approach from this phase will be feasible, like more favorable to give you to the this product as a major product. So here there is another example here. Of course, you are trying to use this sodium borohydride versus L-selectride. That means again you can see the selectivity, as I mentioned there, that if you have a sodium borohydride, you cannot get a good selectivity there. Okay, but once you have L-selectride, now you can see the selectivity will be higher, because once you have this bulky group here, you can see the hydride will not going to approach from this side, the hydride will approach from this side, giving you this product with a very good selectivity. Okay, again it is same for the other substrate as well. Okay, again I think you can see here 86% versus 99.6% exoselectivity. So once you have these dimethyl groups here, now this approach will be less favorable, so the bottom approach will be more favorable, giving to the exo product with 99.6%. There is an example here in this particular substrates, you have this lactone and you have this alpha beta unsaturated ketones, and now if you are using this so you can see this is sterically bulk here. Now this BH can add to the, what is happening, the BH adding to the corresponding ketone here, because the approach you can see you are getting to this particular product as a major product here. Okay, so now if you try to control the diastereoselectivity of the product, you have to try different sterically hindered group, so that you can able to able to control the approach of the H minus. Okay, so here we can also, if you have a chiral center here, now we can able to explain them from this the Falkin conformational model that I think you guys have already learned, that in case of Falkin model we can if you have a stereochemistry here, we can think there is 3 different group here. You see H, R and M. Then if R is a bigger, then you can say this is a large, this is small, this is a medium, and then now if you try to draw this way, the H minus or the nucleophile will approach such a way from this phase to interacting only with a smaller group here, okay, to form this product. So you can see here in case of ethyl, you don't have a good selectivity of this anti versus syn, means the approach of the nucleophile does not have a much more selectivity, still you come to the alkyne, which is a smaller group, to giving you the anti selectivity higher compared to the syn. Okay, so you can see here this will be, because clearly you can see once you see the size of this alkyne is getting smaller, you end up giving to the the corresponding. So that means what is happening, the R size is controlling the selectivity, which is supposed to see from this model also. Then the zinc borohydride, one thing I forgot to mention, that if you have some sort of a SME group or OH next to the carbonyl group here, then that can form a chelate with this oxygen group. So it can form some sort of a chelate here. Okay, in the corresponding tangent state you can see, although you might think that both the SME and oxygen is kind of top of each other, but they are forming a chelate with the zinc. Now that is allowing the H minus to come this phase to facing this H here, which is a smaller group, to giving this product, means this is the corresponding anti product as a major product here. So that's why in the both the cases using SME or OH, you end up getting to the anti product as a major product. Again, I think if you have a sodium borohydride also, you have the OMe group and you are using sodium borohydride also, it was found that in the sodium borohydride also there are some sort of complexation happens and it forms the corresponding anti product as a major product. Okay. The other important thing is, as I mentioned, the sodium triacetyl borohydride, once you have this, so you have a beta hydroxy ketone, and now if you do a reduction of this, there is two different possibility. It can either form this one or it can form, so it could be syn or it could be anti. So this could be, so you can see they are anti or they could be syn. Now that can be controlled using this triacidoxy. So what is happening once you have this triacidoxy? The triacidoxy first actually reacting with this alcohol here. So this is reacting with the boron and throwing up one acetate from that. From there, now if you see this corresponding tangent state, it is actually thrown one of the acetate and this kind of bound with the boron, this bond is formed. So now what is going to happen, if you see this alcohol actually in the bottom phase, now the hydride is going to transfer from the bottom phase where the OH is there. That's why if the hydride is transferring from the bottom phase, correct, then you end up forming this alcohol from the top phase, correct. That's why you end up getting to the anti-product as a major product. Here also, if you use the triacidoxy here, again you can see there is a OH group here. That means you can see that will going to form this OAC. There will be two other OAC and there will be one other H. So now this hydride will be coming from the top phase, giving this this product as a major product, which is shown here. So I talk about the different type of racemic reduction of the carbonyl compound using this different type of borohydride source. Now I am going to talk about the asymmetric. That means the carbonyl have two different phases, the Re and C. Now if you are able to control that, that means now if the oxygen can form some sort of a chelate with this boron which is electron deficient, it can transfer the BH, the H minus through a particular phase of the carbonyl group. Then you can end up getting a enantioselective selective alcohols. So that's why this was developed from, it's called alpine hydride. Again you have already used, you can see this type of compound you have already seen before. So using this alpine hydride you can use, so you can see here what is happening. You can see this is, you have this chiral backbone here in both the side. So now this can transfer the H to this carbonyl group to the bottom phase to give this alcohol as a from the top phase to give this alcohol, okay, with the 62% E. And then there are several other reagents was developed for this asymmetric reduction of the carbonyl compound using the hydride reagent. The one of the other important one is the CBS catalyst, the Kore-Bock-Shibata catalyst, where this catalyst was synthesized the corresponding amino acid proline. Okay, and then once you take this catalyst and then the BH3, the boron actually bind with the nitrogen, form this N plus BH3 minus. So this is become an active catalyst once it is bound with the BH3. So here is a mechanism here from starting from this compound. You can see this is acetophenone analogs. Using the CBS catalyst in BH3, you can able to get 94% EE. So what is happening here, as soon as the boron bind here, this active catalyst generated in situ in the reaction, which now actually once you have a carbonyl group, the carbonyl started coordinating with this boron here. So the carbonyl started coordinating with this boron here. Okay, for once this is happening, now one of the phase of this, so there is two different phase here. One of the phase is getting blocked because if I think in this tangent state it will be difficult to see, but once you see a 3 dimension of this, you can see that this is one of the phases getting blocked. So that will allow the hydride to be transferred to the other phase to get the product with very high enantiomer selectivity. Okay. So in this part I talk about the several different borohydride reagent. I talk about the reduction using boron. I talk about the using the cyanoborohydride, the reductive amination, and also I end up talking about the asymmetric reduction using the chiral borohydride in a catalytic amount. Okay. So there are the references here, and again thank you so much for coming to the class. I am going to see you guys in the next class. Thank you.